Hello everyone, here I'm honored to be able to share our new work, Balanced Multimodal Learning via on-the-fly gradient modulation with you. We noticed that multimodal learning methods achieve very limited improvement with more modality. Then do they fully utilize the multimodal information? Let's look at the boss example. The audio data is noisy and harder to recognize, so we guess such difference between modalities may need to different utilize efficiency during the training. In order to explore if each modality fulfills its potential, we measure the representation ability of encoders with linear probing. As shown in the figure, unimodal performance in multimodal learning, the yellow line is worse than that of the unimodal method, the red line, especially in visual. So we know that under-optimized unimodal representation exists in multimodal learning methods. Now we will analyze the reason how such under-optimized training happens. Let's begin with the concatenation framework. We first give the definitions, encoders phi and its parameter theta, the classifier W and B, and the modality indicator U. We take A and V as examples. The first formula describes the logis calculation in a forward process. The logis score is contributed by two distinctive parts in the way of addition. This means one better modality may dominate the prediction result. And the second formula describes the gradient calculation in the backward process. Similarly, the gradient is also calculated according to the addition of two specific parts. Based on this, we can conclude that if one modality performs better, it may dominate the prediction results and the optimizing process, causing under-optimized representation of the weak modality. That is the imbalanced optimizing we talk about. To illustrate our idea, we'll give an example. Imagine a skating competition. The score of a team depends on the last teammate. Now we have two teammates. A is faster than B. When A arrives at the destination, B just finished half. To improve the team performance, A should help B to speed up. So when A arrives, B can finish more journals than before. It's similar in multimodal learning, where let the dominant modality slows down to wait and help the weak modality so they can make a better teamwork. Now please look at our method pipeline. Totally, we just adaptively modulated the backward gradient in optimizing according to the performance discrepancy between modalities, and such optimizing can be viewed as two steps. First step is on-the-fly gradient modulation. We take SGD optimizer as example. To begin with, we should calculate the unimodal performance S by taking apart the logis prediction into two parts, and then calculate the ratio of two modalities rule. Then the coefficients are calculated as follows. Only the coefficient of the dominant modality is smaller than 1, so it can help to slow down its optimizing to leave more training space for the weak one. After we calculate the coefficients, we can modulate the gradient with them as the red formula does. However, according to former researchers, better generalization ability is closely related to bigger SGD gradient noise strings. But our method maybe undermines the gradient noise strings in the first step. So we introduce an extra adaptive Gaussian noise in the backward gradient to enhance the generalization of the model. In experiments, we first compare with basic multimodal fusion methods and training adjusting methods. As shown in the two tables, our method achieves common improvement under these settings. As shown in the tables, we also make comparison with more mainstream methods in two tasks, and it turns out that our method can boost most mainstream methods more or less. Besides simple classification, we also test its versatility in audio-visual event localization and multimodal representation learning tasks, in which our method brings varying degrees of performance growth. The left figure shows unimodal representation of our method. The blue line supports baselines in both modality, and the right figure shows our method also achieves better multimodal performance. Now let's look at a demo video about how OGMG can help when facing imbalanced multimodal cases.
Ah man, here go Jason shoveling that good old snap.
Obviously, the sample is visually dominated, and our method works better in such case. And in the right figure, we can see that we make a more balanced training. To sum up, we analyze the optimizing imbalance in multimodal learning, which is due to the under-optimized representations, and propose OGMG method to modulate the optimizing gradient, which achieves better results. That's all. Thank you for listening. You can find our poster at 30B.